Okay, so we're glad to have Giulio Lo Monaco talking about Vopěnka's principle in infinity categories. So, let's start, Giulio.
Yes, thank you, John, for the introduction, and thank you for inviting me to give this talk. So today I'm gonna talk about the last article that I wrote, which is about some kind of transposition of Vopěnka's principle, which is classically formulated in terms of properties of one categories, presentable one categories. I tried to transpose the statements to infinity categories and see what happened there and see how they're related to the classical ones. Just a very brief review of the history of this principle. Vopěnka himself initially formulated the principle thinking that it was ridiculously strong, and he believed it to be inconsistent with ZFC. And he even set out to find a proof to this, of the inconsistency of his own principle. And he was very close to publish one, but then just before publication, he found a mistake himself. And then after a couple of years, turned out that it was actually consistent and independent of ZFC. So this is the plan of my talk. First, as in point one, I'm going to talk about the state of the art of what is already known about Vopěnka's principle and some of the consequences in presentable categories. I'm not going to say what the original statement was, because that's really straight out logical, and I feel like my own understanding of it is not deep enough, and like it's not really my field. So I'm just gonna recall the classical statement, a couple of equivalent statements of Vopěnka's principle in terms of presentable categories, and say a few things that are already known. Then, in the second part, I'm gonna give some infinity categorical rephrasing of the statements that I have already given to you, recalled to you in point one, and spend a bit of time telling you how these new statements relate to the older ones, and again, what is known, what I could prove personally, and what I couldn't prove, and why. In point three, I will explore some of the consequences that are already known classically for presentable one categories, and see to what extent they can be generalized for presentable infinity categories. And then finally, I will conclude with some open questions and some views that I have about them. Okay, so we can start with the one-dimensional state of the art. There are, like I said, a number of different ways that Vopěnka's principle can be formulated in. I'm just gonna give two of them here that are the most I think they're the most categorical ones, so the most prone to be reformulated for presentable for infinity categories. So we have this proposition telling us that there are these two equivalent statements. One is that there is no full embedding of the category of ordinals into any presentable category. The other is that there is no proper class of objects in which the only morphisms are the identities in a presentable category. The proof is highly non-trivial, so I'm going to give it here. But this is not new. This was already known. And we say that Vopěnka's principle is satisfied if the two above statements are true. And now, for the sake of brevity, and because I will need some abbreviations later on, I will call the first of these two statements VP and the other VP prime. I choose VP to be the sort of basic one, and to give a superscript to the other, because I think the first statement of these two is the more formal and the easier to generalize to infinity categories, and also because the weaker version of Vopěnka's principle that I'm going to introduce in the next slide has very much the same spirit of this. So here's another statement that is related to these and looks very much like what I'm calling VP now, so Vopěnka's principle. And we say the weak Vopěnka's principle is satisfied if the opposite category of ordinals cannot ever be fully faithfully embedded into a presentable category. And again, for the sake of brevity, I will say, I will call this statement WVP. And well, this proposition motivates the name of this other statement, because we know that Vopěnka's principle implies this weak Vopěnka's principle. Okay, now I want to spend a few words about the set theoretical collocation of these statements. So we know that both Vopěnka's principle and weak Vopěnka's principle are independent of set theory, and they're actually part of the ladder of the hierarchy of large cardinal axioms. And to be more precise, we know, again, this is not new, this was already known, that if we assume the existence of at least one huge cardinal, then we can find a model of the FC in which Vopěnka's principle is true. So it implies, in particular, consistency of VP, or VP prime, which is, as we know, equivalent. And WVP, in turn, implies the existence of a proper class of measurable cardinals, which is actually a quite strong large cardinal axiom. And more than that, I'm not sure about WVP, but VP itself, it not only lies in between some large cardinal axioms, but it is itself a large cardinal axiom. So it is equivalent to the existence of some very, very strong large cardinals that this is not the topic at issue. So I'll just stop here. I just wanted to mention it. And more than that, Wilson has recently, I think a couple of years ago, not more than that, found that the implication, the fact that Vopěnka's principle implies weak Vopěnka's principle is strict, because he exhibited a model of the FC in which WVP is true, but VP is not true. Okay, and now for some consequences of Vopěnka's principle in presentable categories in the one-dimensional case. Just very briefly, let me recall what I'm going to call here localization. This is usually called orthogonality and co-orthogonality class, respectively. I chose to call them localizations, or, well, in the article I actually call them internal localizations, as opposed to the external localization, which is what in literature is known as the Gabriel-Zisman localization of a category. So if we have a category C and a class of morphisms, we say that the localization of this category at S, the class of morphisms, is a full subcategory spanned by all objects that have this extension property expressed in this diagram. That is, whenever F is an arrow in our chosen class of morphisms, and the arrow from A to X is any choice of arrow from A to X, then there exists a lifting from B to X, making the diagram commutative, and this lifting is unique. And dually, if we consider this diagram instead, we have the dual notion, which is the co-localization. Okay, now keeping this in mind, this and the dual of this are the one-dimensional propositions that I focus the most in trying to generalize them to the infinity-dimensional case. So assuming Vopěnka's principle, we take a presentable category K and a full subcategory thereof, and we know that these four statements are equivalent. So A is closed under limits in K if and only if A is the localization of K at a class of morphisms, if and only if it is the localization of K at a set of morphisms, if and only if it is reflective. And moreover, all of these imply presentability of A. This is also already known. I forgot to write it here, but this is due, as far as I know, this is due to Rosicki and Adamek. Now the statements 3 implies 2 and 2 implies 1 are always true. Well, 3 implies 2 is trivial, 2 implies 1 is just a check. It's really just a verification that a limit of objects that are part of the localization is still part of the localization, is still an object of the localization. Moreover, 3 implies 4, which is also not trivial, but already known, and 4 implies 2, because we can choose the class of morphisms to be the units, all the units of the reflection. So the rest of the statements depend on set theory, and in particular, 1 implying 4 is actually equivalent to weak Vopěnka's principle. I think, yeah, this is a typo. I should have written 2 implies 4 and 4 implies 3. These are equivalent to Vopěnka's principle, the stronger version. And moreover, the fact that these 4 statements imply presentability of A are also equivalent to Vopěnka's principle. Okay, so I guess, yeah, this is it for the first part of my talk. And now I'm going to rephrase what I've done so far for infinity categories. VP and WVP are easily rephrased. They just lend themselves easily to just add an infinity sign in front of everything. And we get what I call here VP infinity and WVP infinity. So again, just for the sake of being complete, infinity Vopěnka's principle is satisfied if there can be no fully faithful embedding of the nerve of the category of ordinals into any presentable infinity categories. And weak infinity Vopěnka's principle is satisfied if there is no fully faithful embedding from the nerve of the opposite category of ordinals into any presentable infinity categories. Now, I also would like to rephrase VP prime, which is the equivalent version of the equivalent statement of Vopěnka's principle. In order to do that, we just need to rewrite it in a slightly different form. Now, this statement is really obviously the same thing as VP prime. And it says that in a presentable category K, there can be no proper class of objects in which the morphisms between 2 of such objects are empty whenever the 2 objects are different, and just a singleton whenever the 2 objects are the same object. And this is easily transposed to an infinity categorical statement saying that VP prime infinity is satisfied if in any presentable infinity category there is no proper class of objects in which the morphisms between them are empty whenever the objects are different, and contractible whenever the 2 objects are the same. Now, how do these 3 statements relate to the classical ones? Trivially, we have a diagram of implications like this one. Now, the horizontal implications are already proven. They're non-trivial, but already known from one category theory. And the vertical ones are trivial because, for example, if I take a counterexample of weak Vopěnka's principle and I pull it through the nerve functor, I immediately obtain a counterexample of weak infinity Vopěnka's principle. And the same goes for Vopěnka's principle and the equivalent statement of Vopěnka's principle. Now, this is the diagram so far. We would like to know two things. First, if the vertical implications are invertible. And secondly, if we can have similar horizontal arrows or horizontal implications like the one that we have in the first row. For the moment, I'm just going to answer to the question if the left vertical and right vertical arrows are invertible with an affirmative answer. And this goes as follows. We have to use two lemmas for VP prime and WVP respectively. First lemma says that VP prime is actually equivalent to an apparently stronger statement saying that in a presentable category there can be no proper class of objects such that the morphisms between them are empty if and only if the two objects are different. So this is apparently just half of the statement of VP prime because it only requires that whenever X and Y are the same object, there is some morphism between them, but it doesn't need to be unique. And this is actually equivalent to VP prime. It is also highly non-trivial, so I'm not gonna show proof of this. Now, in order to rephrase WVP, well, in order to show a similar lemma for WVP, observe that what WVP does is prohibiting the existence of a sequence of an ordinal index sequence of objects in such a way that this Hom set is empty whenever alpha is strictly smaller than beta, and a singleton whenever alpha is at least as great as beta. And also in this case, there is a lemma saying that WVP is equivalent to a statement which is apparently stronger than WVP in a way that is very similar to how this statement is apparently stronger than VP prime. In particular, in a presentable category K, there can be no sequence of objects indexed by ordinals in such a way that this Hom set is empty if and only if alpha is strictly smaller than beta. Meaning that whenever alpha is at least as big as beta, there is at least one morphism, but also here we're not requiring any uniqueness condition on this morphism. Now we're going to use these two lemmas and another already known lemma, which concerns the expression of presentable infinity categories as coherent nerves of combinatorial simplicial model categories. In particular, every presentable infinity category can be expressed in such a way, which is quite useful many times. Now, the reason why we need the previous two lemmas is that while the contractibility, while the emptiness of a simplicial set, in particular mapping space in an infinity category, does not imply that the dimension zero, the emptiness of the simplicial set does imply that the dimension zero in particular is empty. This is not true for contractibility. So a simplicial set, a mapping space in our case, can easily be contractible without the dimension zero being a singleton. And this is a problem for the strategy of the proof that I adopted, which is this one. The reasoning for VP prime and WVP is exactly the same, so I just wrote it one time. if we assume that we have a counterexample of VP prime infinity, then by the theorem, this theorem by Lurie, this yields an analogous counterexample up to homotopy in a combinatorial simplicial model category. Now we may at the same time forget the simplicial and the model structure, which leaves us with a presentable category where the half of the statement of VP prime about emptiness is satisfied, but the other half about the remaining Hom sets being singletons is not necessarily satisfied. But now we use the previous lemma about VP prime being equivalent to the apparently stronger statement, and we immediately obtain a counterexample of VP prime. And the same is true for if we have a counterexample of WVP infinity, we obtain in the same way a counterexample of WVP, using, of course, the other lemma. Okay, so what we have done so far is sketch the proof of these two statements. That is, VP prime implies VP prime infinity, and WVP implies WVP infinity. So this diagram at the moment looks like this, where the two we have proven the downward direction of the left vertical arrow and the right vertical arrow. The two horizontal arrows just come as a composition of up, then left, then down in one square, and up, then right, then down in the other square. I want to mention that as for this arrow, the right lower arrow, this is the only proof that I know. I don't know how to directly prove this implication. If I don't know how to directly prove it, I just know how to go up, right, and then down. This is not true for the other. Of course, we can go up, left, and down, but I also know a proof of the other, a direct proof only working with infinity categories, which is simply just an adaptation of the leftward implication here above, which also works for infinity categories. In particular, if we have an ordinal index sequences of objects that constitutes a counterexample of to VP prime infinity, then we can just create another sequence of objects in the same infinity category, in which the object of the new sequence indexed by an ordinal alpha is the co-product of all the first alpha objects in the sequence that we already had. And this immediately already is a counterexample of VP infinity. So there can also be a direct proof of this. Now, what about the rest? We would like to know if this is a invertible, which is equivalent to saying that this is invertible. And well, this is the only thing that remains to be done in this diagram. So yeah, the only thing that remains to fill is whether classical Vopěnka's principle implies infinity Vopěnka's principle. The answer is, at the moment, I don't know, but I think I have good reasons to believe that that implication is true. And there are at least, well, for one thing, the fact that the same is true for weak Vopěnka's principle is motivating, but I also have at least two more technical reasons to believe that. One of them is that many of the one-dimensional proofs of already known statements about Vopěnka's principle substantially depend on the following proposition, saying that every accessible category can be fully embedded into the category of graphs, so that Vopěnka's principle is equivalent to the same statement, just not taking place in any presentable category, but just in the category of graphs, and then handling graphs very explicitly in order to create counterexamples to the other equivalent statements of Vopěnka's principle. Now, this proposition admits an infinity categorical analog, which leads me to think that maybe it is possible to perform some equally explicit calculations with some sort of infinity categorical graphs, and obtain in particular, I should go back, an inverse of this arrow, which would automatically imply an inverse to this arrow. Okay, so this is one of my reasons. And the other is that many categorical results that depend on VP generalize to infinity categories, still just assuming VP and not even mentioning VP infinity. In particular, the statement that I showed you before during the first part of the talk with the four equivalent conditions for a full subcategory of a presentable category does generalize to infinity categories, only assuming VP, the one-dimensional form of VP. Okay, I now want to talk about this this embedding of any accessible infinity category to what I'm calling here informally infinity categorical graphs. So if G is the category having two distinct objects and two distinct arrows between them, which is the indexing category of graphs, basically, then for every accessible infinity category K, there is a full embedding from K to spaces, functors from G to spaces. And I would like to show you some, not the full proof, but at least a strategy of it. First, we would like to reduce the statement to a more specific one, reducing K to something of a specific form, and reducing also S to the G to something easier to handle. So first, about the domain of this functor, every accessible infinity category is embeddable into a presentable one, basically by definition of accessibility. Next, every presentable infinity category, like I said before, a couple of slides back, is expressible as the underlying infinity category of a combinatorial simplicial model category. And now we have a result by Duggar that we're using in an unconventional way to see that this is that a combinatorial simplicial model category is equivalent. I forgot to write equivalent here, but it is equivalent to a simplicial full subcategory of simplicial sets to the C, where C is ordinary. Now, why am I using the word unconventional here? It is unconventional because Duggar's theorem states that every combinatorial model category, whether it is simplicial or not, is a left Bousfield localization of something of this form. But now there are two different statements of it. One, which is much easier to prove, which applies when our model category is simplicial. And the other, which is harder to prove because we don't have all the simplicial machinery, that applies when the model category is a general, possibly non-simplicial model category. Now, by Lurie's theorem, we know that we're dealing with a simplicial model category, but we actually want to use the other part of the statement, the poorer one about non-simplicial categories. And the reason is that we want to obtain C to be an ordinary category. We don't want it to be simplicial here. And the reason of this will be clear in the next slide. Now, as regards the codomain of this to be constructed embedding, we simply need to observe that the infinity category spaces to the G can be seen as the underlying infinity category of this model category, with either the projective or the injective model structure. Now we're reduced to exhibit a simplicial full embedding from simplicial sets to some arbitrary ordinary category to simplicial sets to G, which we do quite explicitly. Now, since C is not simplicial, this category is not the category of simplicial functors, but it is just the category of all functors, which allows us to shuffle C and delta op around, forgetting the delta op is actually sort of the basis of the enrichment of simplicial categories. And we just forget for the moment that simplicial sets is the enriching category. We just treat it as ordinary functors from delta op to sets. So doing this bit of shuffling of C and delta op, we can see that an object of this functor category is a sequence of functors like this from C to set, indexed by natural numbers, with natural transformations between them corresponding to the errors of delta op. And the same is true analogously for this functor category. Now, by the classical statements, since set to the C is a presentable, well, in particular an accessible category, then there is a full embedding that I'm going to call gamma from this to set to the G. And now we define our new embedding from S set to the C to S set to the G, just degree wise. Okay. Which for the moment only gives an unenriched functor, which is not enough for our purposes. So we need to first make delta into a simplicial functor, and secondly prove that delta is actually a full embedding as a simplicial functor, which we will do both at the same time. So what we have here on the left is the nth dimension of the simplicial set of morphisms from F to G, and in S set to the C. And what we have on the right hand side is the nth dimension of the simplicial set of morphisms from delta F to delta G in this other simplicial category. So we need a functor. We need a natural function from here to there, which is compatible to all the maps in the degeneracies and the phase maps. So first, we know that we have an isomorphism here, which is a direct consequence of the fact that we have an isomorphism. We have a dimension y-wise isomorphism due to the fact that gamma is known to be a full embedding. We only need to connect these remaining parts. What I will do is define a function from this object here, delta f times delta n, to the functor delta applied to f times delta n, and show that this induces an isomorphism. So for each natural number that is an element of delta op, observe that we have an isomorphism like this one, just because we're working in sets. So we can express a product with any set, in a set of maps in this case, as the co-product of equal copies of the other object indexed by the same set. This is just, well, you all know this. And we do the same on the other side, and then apply gamma to the isomorphism. So now, by universal property of coproducts, we have a natural map like this. And since this map is natural, it also induces a a natural transformation, just like the one that we wanted. Now, the last part of the proof, I'm not going to show the details. It is not trivial, I would say, but also kind of straightforward. It doesn't require too much fantasy to be proven. This induces a bijection of mapping spaces, just like the two, sorry, mapping sets, just like the two mapping sets that were missing that we wanted to connect. Now observe that theta itself is basically never an isomorphism. So it only induces an isomorphism by precomposition when the codomain here is in the form delta G. It has to be in the image of the functor delta. Yeah, so we both found a map and found that it is an isomorphism, and it is natural, so it is compatible with all degeneracies in phase maps. So in particular, we have an induced isomorphism of mapping simplicial sets, and the proof is complete. Now, there are at least two things about this proof that personally I was surprised by. Two features of this proof. One is that when we find the category C, we have all the interest in C not being simplicial, which is the only instance that I can think of in which we actually prefer not to have something simplicial. It's usually, in my experience at least, it is usually much simpler and much more handy to have to assume that all things are simplicial. But if C were to be simplicial, this proof wouldn't actually work, because we wouldn't be able to shuffle C and delta up around, and we wouldn't be able to consider set to the C alone as a category without talking about delta op. And the other that I find surprising feature of this proof is that is the key part. So this central part, after reducing to the case of S set to C and S set to G, this is very one-dimensional. It is a very classical looking proof, in my opinion. It has really basically nothing of infinity categorical or of enriched categories. Now, compared to the classical theorem, there's still just one thing missing that as of yet, I couldn't manage to prove. In particular, in the classical version, the full embedding lands in all functors from G to set, such that the map that sends an edge of a graph to the pair given by the source and the target, the edge, is a monomorphism. So there is at most one edge for every pair of given vertices. And at the moment, I have no proof of anything similar to this for the infinity dimensional case. But if we could prove that our delta has the same property up to homotopy, then this would allow an adaptation of the proof VP prime implies VP to the infinity case. So we would automatically, not automatically, but like very quickly we would have VP prime infinity implies VP infinity. The reason of this is that in the one-dimensional proof that VP prime implies VP, we're in one of the key steps, we're using that for any given cardinal, if I have a counterexample of VP, so on ordinal index sequences of graphs satisfying that condition, for any given cardinal, these graphs are definitively strictly bigger than the cardinal. So they keep increasing. They can never be, but they cannot be all bounded by one cardinal. They keep increasing indefinitely. And we use that fact in a substantial way. So we would like to have something similar up to homotopy in the infinity case, which would allow for an adaptation. Now, word to consequences for presentable infinity categories. So, particular, this is a generalization of the one-dimensional fact, the one-dimensional proposition that I showed you before. First off, this is just part of that proposition. Assuming WVP, which now know to be equivalent to WVP infinity, then a full subcategory of presentable infinity category closed under limits is reflective. This is like I wrote here, this is just a straightforward adaptation of the one-dimensional proof. It is basically a proof by contradiction. Assuming the existence of a full subcategory which is closed under limits but not having a reflection, then we can obtain a counterexample of WVP infinity, just in the same way as we do that in the one-dimensional case. With just a little peculiarity, that is, in the one-dimensional world, we know that if our full subcategory happens to be the limit closure of the small full subcategory, then this is always reflective without assuming any set theory, which I couldn't prove in the one-dimensional case. Other than that, the theorem, the proof of the theorem is really the same. And now we got to the more general theorem. Assuming VP, note that I'm only assuming VP, just like I said before, I'm not assuming VP infinity. Consider a presentable infinity category K and a full subcategory A, then the following are equivalent, and these are exactly the same thing as in the one-dimensional statement. And any of these conditions implies that A is presentable, just like in the one-dimensional case. Now, the strategy of the proof is similar. Well, it is exactly the same for all the statements that are independent of set theory. In particular, 3 implies 2 trivially, and 2 implies 1 exactly in the same way as in the one-dimensional case without set theory. 4 implies 2, again in the same way. 1 implies 4 with weak Vopěnka's principle, which is the previous slide. And now by result by Lurie, 3 is equivalent to the condition that A is presentable. And the rest of the proof, whose strategy, the strategy of which I'm going to show you in the next slide, shows simultaneously that 2 implies 3 and presentability of A. And here it goes. If we express K, as we know that we can do, as the underlying infinity category of a combinatorial simplicial model category M, then we have a theorem by Chorny saying that Vopěnka's principle implies that we can left Bowles field localize at any class of morphisms, not necessarily a set, and still obtain a combinatorial simplicial model category. And the way that Chorny does that is by showing that any left Bowles field localization at a class of morphisms is actually a left Bowles field localization at a small set of morphisms. And then just apply the classical result. So we obtain A as the underlying infinity category of a left Bowles field localization of M, which by Chorny's theorem we know to be a combinatorial simplicial model category itself. And well, this is the end of it. we have proven at the same time that A is presentable because it arises as underlying a combinatorial model category. And also it is a Bowles-free localization, so it is reflective. Now, why is VP enough? Why do we not need VP infinity in order to prove this theorem? The reason is that combinatorial model categories are very well behaved in such a way that many strict constructions, at least definitively with cardinals that are large enough, in fact already encode the corresponding infinity categorical ones. For example, filtered colimits and compactness. These are notions that, again, not for any cardinals, but for large enough cardinals can be already encoded in strict filtered colimits and strict compactness. Now, this is a dual, a partial dual of the previous proposition that has been proven in the one-dimensional world about co-localizations instead of localizations. And of course, we assume here the A to be closed under co-limits instead of limits, and to be co-reflective instead of reflective. And under VP, these three are equivalent and imply that A is presentable. Now again, 3 implies 2, which implies 1, always without set theory. And I couldn't manage to generalize all of this to the infinity categorical world. I could only manage to prove that if we're assuming VP, we have that 2 implies 3. So 2 and 3 are equivalent. But I don't know if 1 also implies 2 and 3. The proof of the infinity categorical version of the segmented issue is really in the same spirit. The strategy is the same. We reduce everything to combinatorial model categories. But there is a little subtlety, which is a sort of a mismatch between left and right Bowles-free localizations. Without assuming set theory, we know that left Bowles-free localizations can normally be performed with respect to sets of morphisms, whereas right Bowles-free localizations can be performed with respect to classes of morphisms of all the morphisms that lift uniquely on the right of sets of objects. So the smallness condition is given to objects instead of sets. Objects for the right case and sets for the left case. But this mismatch does not exist anymore if we're assuming VP, because we have this proposition saying that under Vopěnka's principle, then right Bowles-free localizations of combinatorial model categories correspond with those in the form above. So the right Bowles-free localizations of this form exhaust all right Bowles-free localizations under VP. Okay, the reason why this is not a full dual to the other big theorem that I generalized is that these conditions can never be assumed to be equivalent to A being the colocalization at a class of morphisms, not even under Vopěnka's principle, because here's a counterexample that does not assume any set theory, provided to me by Rositsky, which shows that the colocalizations at classes of morphisms are never the same as colocalizations at sets of morphisms, not even under VP and not even in the one categorical world. So in the category of groups, if we take the class of all morphisms, then the corresponding colocalization can easily be shown to be just a singleton of the zero group, but this can never be expressed as a colocalization at a set of morphisms. A little remark about the last proof. There is a little annoyance, a little more difficulty in proving the theorem about co-localizations rather than localizations, because we cannot assume that all of our categories have a Quillen model structure. We can only assume that they have a right semi-model structure. And the reason of this is that we know that K underlies a model category which is left, so that it allows left Bowes-Field localizations to be still Quillen model categories, but it is not right proper. So we can still perform right Bowes-Field localizations, but they're no longer Quillen model categories. They're just semi-model categories, right semi-model categories. This is a little annoyance. It is nothing substantial, but there are a few results that just have to be reproven for the right semi-model case. Some others cannot be reproven. They're simply false in the right semi-model case. But what can be proven turned out to be enough for the sake of the proof of this theorem. And now I will conclude with some open questions about all of this. First, of course, we have whether VP is equivalent to VP infinity or not. Now, as I said, I'm convinced that there should be an affirmative answer to this, which is just out of reach. I can almost see it, but well, I don't have a technical proof of it. Related to the first open question, we have what I mentioned during one of the first slides. Vopěnka, weak Vopěnka's principle can be formulated by preventing descending chains of objects plus some conditions of morphism between them that do not mention contractibility or the property of being a singleton in the one categorical case. But as of now, there is no similar formulation of VP. So what I would call a similar formulation of VP would be preventing an ascending chain of objects plus some conditions of morphism between them that do not mention contractibility, which is not the case at the moment. We have to talk about contractibility or the property of being a singleton. The reason why this is strictly related to one is that if we were to have a formulation of VP in this spirit, then the proof that WVP is equivalent to WVP infinity would immediately transpose to a parallel proof, proving that VP is equivalent to VP infinity, just in the same way. Now, a more general open question is if there is a special adjoint functor theorem for infinity categories. And the reason why I'm interested in this in regard to Vopěnka's principle and weak Vopěnka's principle is that in the one case, like I mentioned a little earlier on, the limit closure of a small full subcategory of a presentable category is always reflective without assuming any set theory. But the proof of this uses the special adjoint functor theorem for one categories. Whereas there is no special adjoint functor theorem for infinity categories. So in order to prove this, I had to resort to the more general case of a limit closed full subcategory, of a general limit closed full subcategory, which requires weak Vopěnka's principle. So I don't know if it is possible to prove reflectivity of a limit closure of a small full subcategory without any set theory. And also the part that was missing from the last theorem that I could manage to generalize is whether it is true that under under infinity Vopěnka's principle, then the co-limit closure of a full subcategory of a presentable infinity category is co-reflective, because the one-dimensional proof of that, of the corresponding fact, also uses the special adjoint functor theorem. Now, unfortunately, I don't know if this is true, but I have very low expectations about an infinity special adjoint functor theorem, because the classical statements and, well, the classical proof of this theorem relies in a substantial way on the fact that it is easy to detect monomorphisms in one categories, whereas the behavior of monomorphisms in infinity categories is a little poorer. The reason, what leads me to say this is that monomorphisms with a fixed codomain do form small sets in a presentable infinity category, but they're not easily detected. And if we apply the detection method of monomorphisms for one categories to infinity categories, we're only talking about I guess 0 truncated morphisms, which no longer form small sets. So there's this mismatch that's I don't know how to fill. Well, this is the end of my talk. So thank you for your attention.
Okay, thanks very much for a nice talk, and we have our usual silent round of applause. So thanks, Giulio. And if anyone wants to ask a question, go ahead.
Yeah, I can ask a question. Sorry, the sound is very loud. Right. Anyway, so you characterize both the BP and the BP infinity as a corresponding requirement that localizations of classes of maps, localizations of set of maps, right?
Yeah.
Now there is an interesting special case in the dichotomy between ordinary category theory and infinity category theory. Namely, if you restrict your attention to left exact localization, right? So we know that if we have a, let's say, two-sheet category, then every left exact localization is in fact already an accessible localization. So it's the localization of the set of maps. And I think that's true for every presentable category as
well.
Yeah. The same is not known to be true in the infinity category, right?
Exactly.
Is there, so you could have, so there would be some statements, every left exact localization is presentable category. Infinity category is already the localization of the set of maps. That's a weaker or a special case of you know how strong that is? Is that strictly weaker? Does that fit into any of those hierarchies in any way? Have you thought about that?
So the question is, if I know how to prove under Vopěnka's principle that every left exact localization is accessible.
No, I mean you get that, right? Because every localization is accessible. There's
yeah.
I would present the category, but the question is that thing? I mean, how? I mean, it's not apparently a weaker statement, but is it, where does it fit into those hierarchies? Is it equivalent to something else in that realm of other statements equivalent to BP infinity? Is it maybe not even strictly weaker, maybe just as strong? I don't know. I mean, it's an interesting special case. That's what I'm saying. I don't know where it fits into in all your considerations.
I'm not sure. In particular, well, as I said, well, going back to here, for example, one of the some of these statements are equivalent to either WVP or VP, but I don't know if the infinity categorical versions of these statements are equivalent to WVP and VP respectively. I just know that they're consequences of them. Mm-hmm. So I guess this is related but the answer is I don't know. I couldn't prove it.
Yeah. Anyway, I would think that that would be like an interesting
Interplay.
statement. Yeah, and a statement that is interesting to many people to know whether what do I have to explain? What is the weakest thing I have to explain so that I get that every left exact localization presentable to the category is already accessible?
I'm sorry. Can you say this again? The
The
audio is very disturbed.
Yeah, I know. What is the weakest thing I have to assume, or what is something I have to assume, so that every left exact localization of a presentable infinity category is itself accessible? So it's the localization of the set of maps already. That would be an interesting question, I think.
Yeah, I should think about it, I guess.
Any more questions? So there was a question in the chat. Carlos, maybe I mentioned it. Would 4 be easier for stable infinity categories? Number 4.
There is a lot of noise here, but I mean, when in stable categories, you normally have a good correspondence between reflections and co-reflections. That's why I may suggest that perhaps deciding on co-reflectivity of co-limit closed classes might be easier to infer in stable infinity categories. Could this be true?
So I'm sorry, what is the question precisely?
Your open problem number 4, I asked whether it has an easier answer in stable infinity categories.
I expect it does. I don't have a proof of it, but I certainly expect it does. It does have an affirmative answer.
And my second question is what you take as definition of an infinity category. Because if you start as Luri does, he says that an infinity category is a simplicial set such that blah, blah. Then I think that going to finite, to fine set theoretic issues with this definition doesn't work. So which definition do you take for an infinity category?
Luri's definition. Up to size issues. Like, I mean, yeah, it's of course it's supposed to be a simplicial class rather than a simplicial set. So a functor from delta up to classes, satisfying the
that's not what he says. He says it's a simplicial set. So I'm not sure.
Yeah, but he also assumes multiple universes. So it is basically the same as assuming classes.
Okay.
No, but universes cannot help you. This is just a kind of shift, yes. Just shift it up.
Sorry?
Universes cannot help you. This is the kind of.
What do you mean? I think they can.
No, just simply go from sets to classes. So that's the question remains, yes.
Well, if I assume universes, then if I want something to be large, I just go to one universe above.
Yes, from sets to classes. If you want, you can go from classes to hyperclasses and so on. But I think the original question remains, yes. Because if you say that it lives in the next universe, the same thing, this is a class, yes.
Yeah.
So that there could be some threads there or not.
Not that I can see, at least.
Okay, if we can freely change universes, then all localizations exist with respect to classes, whatever. Of course.
Oh, okay. Well, when I say classes, if I'm assuming universes, whenever I say classes, of course, I mean sets in the same universe as all the stuff that I'm calling large.
Okay, yeah. Thank you.
Yeah, can I ask one question? It's probably quite stupid. just in your in your various implications, you don't mention graphs anywhere, but then you use graphs in the proofs, say, right? You use an embedding into a category of graphs. And I'm just wondering how essential graphs are to that, how much flexibility there is, what else you could take. Like I could imagine in the infinity world, you might replace graphs by semi-simplicial things, or I don't know. I'm just wondering if there's
I did think of that. I was thinking of semi-simplicial sets instead of infinity graphs. But well, I also stopped there. I couldn't prove the existence of any embedding to semi-simplicial stuff. To try to answer your question, I don't know how essential that is in the one categorical case, but the only proof that I know, which is in Adamek and Rositsky's book, really relies on that. So I don't know if it is the only way that we can prove these facts, but it is certainly the only one that I know, and I'm sure if there is another proof that dispenses with the embedding to graphs, it should be quite a bit more complicated.
Okay.
Just may I ask, Giulio, there are other equivalents of Vopěnka's principle in one categorical world. Notable is that any full subcategory of a locally presentable category to inclusion preserves lambda filter collimate of some lambda. Yes.
Yeah.
So one can ask, of course, the same thing for infinity categories, and then maybe this your replacement of graphs by simplicial graphs would be helpful. Have you thought about this?
I thought about the equivalent statement of Vopěnka's principle that you just mentioned.
Yes.
I didn't think yet of proving it through the simplicial graph method, just because the simplicial graph, the embedding to simplicial graphs is very recent. I came up with it like last week. But yeah, there is definitely time to try to use it in some more ways.
Okay. Any last question? Well, if not, then let's thank Giulio again.
Thank you.
And so that's our last talk before summer, and there's a talk of Charles lined up in August, and then in September sometime we'll start again, and some of it might be in person. Then we haven't figured that out, but we'll be in touch about what way it continues. So okay, so that's we can stop recording.